Hello there, Mr. Sutton here, bringing you the AB Calculus 414 Extra Practice Number 2 solutions on related rates. For this problem, the radius of a circle is increasing, and at a certain instant, rate of increase in the area of the circle is numerically equal to twice the rate of increase of the circumference. What's the radius of the circle at this instant? Alright, so we have multiple rates of change going on, which means this is going to be a related rates kind of problem. So we're going to try to set up some equations and take the derivative of things with respect to time, and then hope that we're going to be able to unsort this mess. So this is a little bit tricky getting started. This is actually a really tricky one because it involves two different formulas. So we're talking about the area of a circle, so A equals pi r squared is a good place to start, but the circumference is also involved. So we have to remember that circumference is 2 pi r. And let's see here, I'm going to go ahead now and take the derivative of the area formula here. So taking the derivative with respect to time, derivative of A is dA over dt. Derivative of pi r squared, that's going to be 2 pi r times dr over dt. Everything is a function of time. And at some point, we want to know what the radius of the circle is. So eventually, we're solving for this r value. But if you think about it, we don't really have enough information to do that. They did tell us that the rate of increase of the area is numerically equal to twice the rate of increase of the circumference. So we know a little bit about dA over dt. It's somehow related to the rate of increase of the circumference. But they didn't really tell us a whole lot else that would help us here. So when in doubt, let's just go to this other circumference formula, take the derivative of that, and hope that it gives us something we can use. So derivative of this one, derivative of c is going to be dc over dt, and derivative of 2 pi r, that's going to be 2 pi times dr over dt. So again, they told us that the area was numerically equal to twice the rate of increase of the circumference. So dA over dt could be expressed as 2 times dc over dt, which doesn't seem super helpful right away, but if you think about it, dc over dt is all this stuff over here. So instead of writing 2 dc over dt, we could write 4 pi dr over dt. Now, the reason that's helpful, if you're trying to solve for r, we have a dr over dt on both sides of the equation. We could cancel those out if we're allowed to divide both sides of the equation by dr over dt. There's just one catch. dr over dt is kind of a variable, and we're not supposed to divide by variables because there's a risk that we might be dividing by 0. So how can we legally get away with that in this situation? Well, here it helps to look back at the problem where they said the radius of the circle is increasing. Well, that means that dr over dt is positive. If it's increasing, if the radius is increasing, its derivative must be positive, greater than 0. And that's important because if the radius is greater than 0, then it's not equal to 0. We're guaranteed it's not 0. So because the radius prime, the rate of change of the radius, is not 0, we can therefore divide both sides by dr over dt. We're also going to divide by 2 pi. So that's going to cancel out the dr over dt's, and we're just going to end up with 2 on the right side. So r equals 2 then, final answer, choice D. For this problem, we have a region bounded by 2 circles, and the long and short of it is we have these 2 different radii increasing or decreasing at different rates, and they have certain values at a certain point in time. Eventually, they want us to figure out the rate of change of the area of this shaded region when all is said and done. So because we have all these related rates, this is a related rate problem, we're going to have to set up an equation that ties all of this stuff together and then take the derivative with respect to time to figure out the value we're missing. So what are we looking for exactly? Again, we want the rate of change of the area of this shaded region. So let's start by writing an equation that gives us just the area of the shaded region. To get that, I'm going to need to involve the areas of 2 different circles. So I'm going to have the area of the larger circle, which is going to be big pi, or pi times big R squared. And I'm going to have to subtract the area of the smaller circle, which is going to be pi times little r squared. So let me go ahead and take the derivative of this whole thing with respect to time now. derivative of area, that's going to be dA over dt. And each of these is going to be its own power rule. So we're going to have 2 pi times r times d big R over dt. Over here, this is going to be minus 2 pi little r times d little r over dt. And now we hopefully have something to plug in for all these different r's and dr's. So for big R, and we've got d over dt, we're solving for that. For big R, they actually told us that that was 4 inches in the problem. So we've got 2 pi times 4 times, well, what's big d big R over dt? They said that the radius of the outer circle, big R, is increasing at a constant rate of 2 inches per second. So that means positive 2 is d big R over dt. Now we're going to subtract 2 pi times little r, which they told us was 3. And what's d little r over dt? Well, now they said the radius of the inner circle is decreasing at a constant rate of 1 inch per second. So that's actually going to be a negative 1. Putting it all together now, we've got, let's see here, 2 pi times 4 times 2. That's going to be 16 pi minus, well, we've got minus minus, so it's actually going to be plus. And this is going to be 6 pi over here. So that's a grand total then of 22 pi, which is going to be choice D. And the units on this, if you were wondering, I mean, they didn't require it, but since it's dA over dt, area is in square inches, time is going to be in seconds, so this would be square inches per second. In any case, choice D. For this problem, we have a little bit of a backstory. This is a part of a free response here. We have some oil leaking from a pipeline on the surface of a lake, and this makes an oil slick whose volume is increasing at this constant rate, 2,000 cubic centimeters per minute. And this oil slick, it's kind of interesting. It takes the form of a right circular cylinder, and it's both the radius and the height are changing with respect to time. They also gave us the formula for the volume of a right circular cylinder, so this is probably going to be useful in a minute. So now the part of the question we actually have to answer, at the instant when the radius of the oil slick is 100 centimeters and the height is 0.5 centimeters, they're telling us the radius is increasing at a rate of 2.5 centimeters per minute. Here's the question. At this instant, what's the rate of change of the height with respect to time? All right, so we have multiple rates of change going on in this one. We have the rate of change of the height. That's what we're actually looking for. And they also gave us, in the beginning of the problem, the stem of the problem, they gave us the rate of change of the volume. And further down in this part A here that we have to do, they gave us the rate of change of the radius. So we're going to set this up as a related rates problem. We're going to come up with an equation that ties everything together, differentiate that with respect to time, and then we'll be able to incorporate all these rates of change and find the one that we're looking for. So the formula that ties everything together is clearly this volume formula. It has volume, radius, and height, all the friends that we're looking for here. So let's go ahead and take the derivative of this formula. So on the left side, derivative of v, that's going to be dv over dt. And on the right side, to take the derivative of pi r squared times h, I'm going to use the product rule on this one. So let me bust out the box and ribbon here. My two factors, we've got pi r squared and h. Derivative of pi r squared, that's going to be 2 pi r times dr over dt. So everything gets a tail with a dt because everything is a function of time in these problems. And then h derivative is going to be dh over dt. Now this is what we're actually trying to solve for when all is said and done. So using the ribbon to multiply all this out, we've got 2 pi r dr over dt times h. So I'll just stick the h in the end of all that. And then going the other way, we have pi r squared times dh over dt. And we're adding all that stuff. And at this point, it's time to start plugging in what we know. So again, we're solving for dh over dt. That's the only thing that we don't have to plug anything in for at this point. So dv over dt, what's that going to be? Well, in the beginning of the problem, they said that our volume was increasing at a rate of 2,000. So that's 2,000 out there. R, well, they said the instant when the oil slick is 100 centimeters, the radius of the oil slick. So that's 100 for R. And dr over dt, that's the rate of change of the radius. They said that was increasing, constant rate of 2.5, so that's positive 2.5 for dr over dt. And then finally, h, the height at this exact time, that's the 0.5 that they mentioned right here. So we'll throw that in as well. And we have another term here. We have pi r squared dh over dt. Again, r was 100, so let's throw that in there as well. And at this point, we're going to go ahead and solve for dh over dt. So let me clean things up a little bit first. This whole expression here, well, let's see, 0.5 times 100 would be 50. 50 times 2 pi is going to be 100 pi, times 2.5 would be 250 pi. So we have 2,000 equals 250 pi. Over here, this is going to be 10,000 pi dh over dt. So solving for dh over dt, let's go ahead and subtract 250 pi from both sides, and then we can divide everything by 10,000 pi. And we could just leave it like that and put some units on it and call it a day, or we can go to the calculator, which I will do now. So plugging all that in my fancy fraction form here, that comes out to 0.039 if I round it off. Now, what's the units going to be on this? Because that's what they really care about, along with something numerically equivalent to the answer. Well, since I'm estimating or getting the rate of change for the height, dh over dt, height is measured in centimeters, time is measured in minutes, so this is going to be centimeters per minute to go with our 0.039. On this problem, we've got a spherical balloon and a whole bunch of information about it. For this part of the question, they want us to find the rate of change of the volume of this balloon with respect to time when t equals 5. So if we're doing this with respect to time, I mean, if you look at the formula for the volume of the balloon right here, there's no t in here. There's an r, there's a v, but there's no t. So to figure this out, we're actually going to have to differentiate this with respect to time and then hope that we can come up with something for everything involved in this. So we've got dv over dt, and now differentiating r also with respect to time. On the right side, we're going to have 4 pi r squared times dr over dt. So here's where we have to actually look back at all this backstory on the question. If I want to find dv over dt, that means I need to know what r and dr over dt are. Well, the r that they're talking about, that is the radius at the specific point in time that this problem takes place. That is time 5 right here. So what's the radius at time 5? If you read through all this craziness, they say the radius of the balloon is 30 feet when t equals 5. So for this r, we're going to actually plug in that 30. And then for dr over dt, that's the rate of change of the radius with respect to time. So that's equivalent to this r prime of t up here in this table. At time 5, that's the crucial key here, at time 5, they said that r prime of t was 2.0. So that's what we're going to plug in here, because this whole problem takes place when time equals 5. So plugging in 2.0, and at this point we can just multiply everything out. So this was a no calculator problem, I believe. You could simplify it if you wanted to, or you could just head straight to putting units on the end of this, since this is all constants. If you do multiply this out, well, let's see, 30 squared is 900 times 4 pi, that's going to be 3600 pi, times 2, now you have 7200 pi. But really, whether or not you simplify, the most important part of this is the units. What units should this be in? Well, we're finding dv over dt. So just looking at this in fraction form, volume is measured in this problem in cubic feet. Time is measured in minutes. So this is going to be in units of cubic feet per minute. For this free response problem, I'm given this curve here, and my first task is to show that the derivative of this thing is this other expression. Well, since I can't isolate y, I'm going to use implicit differentiation. So going from left to right, derivative of 2x squared is going to be 4x. 3y squared, that's going to be 6y. But since y is being treated as an inner function of x, I have to multiply by the derivative of this inner function, which is dy over dx. And I only have to do that for y because y is a function of x. If you did a dx over dx, it would just be 1, so it really wouldn't be worth it. All right, so moving on now. We've got this product rule we're going to have to do for the negative 4xy. Let me set up my box and ribbon to help me with that. So I've got negative 4x and y. Derivatives are going to be negative 4 and dy over dx. Multiplying that out with the ribbon, I've got negative 4y minus 4x dy over dx. And then all of that is going to equal the derivative of 36, which is 0. All right, let me get all the stuff with dy over dx on one side and everything else on the other side. So this 6y dy over dx, that can stay on the left. So can the negative 4x dy over dx. This 4x here got to move over to the right side. And we'll do that by subtracting it. And then this 4y, we're going to add that over to the right side. So now I can factor dy over dx out of the left side, leaving me with just 6y minus 4x. And if I divide both sides by that parentheses, I've got dy over dx all by itself. Unfortunately, I haven't actually finished the problem yet because this expression and the expression that they wanted don't match up. It's algebraically equivalent, but you actually have to make them match up. So one thing to notice is that we could write this as 4y minus 4x, and it would be just the same. We can also reduce everything here by 2. So that would be 2y minus 2x on top. And down here we're going to have 3y minus 2x. And that matches exactly with what they wanted. For this part of the problem, they want us to find the slope of the line tangent to the curve at each point where x equals 6. So recall from part A, the derivative requires both x and y values to figure out what dy over dx is. We already have the x value, it's 6, but we need the y value or y values to go with it. How do we get those? Well, we go back to the original equation that relates x and y. So I'm just going to plug x equals 6 in for all the x values here, and then I can turn around and solve for y. So I've got 2 times 6 squared plus 3y squared minus 4 times 6y equals 36. And then cleaning this up a little bit, we're going to have 72 plus 3y squared minus 24y equals 36. And we can clean it up a little bit more. This looks like a quadratic, so let me just get everything on one side here. I'm going to write 3y squared minus 24y, and then we'll subtract the 36 to be over here, so we'll have a plus 36 left over on the left side, and then equals 0 on the right. This looks like I ought to be able to factor it, so let's try that. If I take a 3 out of everything, that leaves me with y squared minus 8y plus 12. All of that equals 0. And two things that multiply to give me 12 and add up to negative 8, we can factor this into y minus 2 and y minus 6. All right, so that means that our y values are going to be 2 and 6. So we just need to figure out now for the points 6, 2 and 6, 6 what the dy over dx equals. So at this point, let me rewrite what I had in part A. Now they gave this to us. This was their dy over dx formula. We just proved it, but they already gave it to us. So all we have to do is plug our 2 points into this formula and let the chips fall where they may. So I'm going to evaluate first at the point 6, 2 right here. So evaluating this dy over dx at this point, in the numerator I'm going to have 2 times the y value 2 minus 2 times the x value 6 all over 3 times 2 for the y value minus 2 times the x value 6. And what's that going to come out to? Well, upstairs I've got 4 minus 12, which is negative 8. Downstairs we've got 6 minus 12, which is negative 6. And if I want to, I could reduce that to 4/3. I don't need to reduce it. Honestly, I could have stopped at this point here where I had all constants, but I just like to keep going. I wouldn't do that on the actual exam, though. All right, so the other thing we need to find out is the slope at the point 6, 6, because that was the other y value that went with the x value 6. So evaluating at 6, 6, well, this will be a little bit easier because these are both the same number now. So we've got 2 times 6, it's always going to be 6, minus 2 times 6, over 3 times, and this is the y value 6, minus 2 times the x value 6, as if it makes a difference. So up here, we see right away we've got something minus itself. That's going to be 0. Downstairs, we have 18 minus 12, which is 6. But honestly, as long as you don't have 0 in the denominator, this whole thing comes out to 0. On this next part of the problem, they want us to find a positive value of x at which our curve has a vertical tangent line. So for vertical tangent lines, we're talking about a perfectly vertical slope. And if we're talking about slope, we should talk about the dy over dx formula that they gave us back in part A. So here it is again. Now, if I want a perfectly vertical tangent line, that means I want the slope to be non-existent, undefined, which means that I need the denominator to have a value of 0. So I'm going to really start this by setting 3y minus 2x equal to 0. And at this point, it looks like it's going to be tough to solve for x because I'm going to get something with a y in it. So it's becoming clear to me now that I'm going to have to solve a system of equations in order to figure out x or y. So I've got this equation right here, and what other equation could I use to figure this out? Well, the only other equation I have here is the original equation up here. So I'm going to try doing a little substitution. Now, eventually, I want to solve for x. So I'm actually going to isolate y in this equation so that I'll get something in terms of x that I can plug in up in the original equation. So let's see here. If I add 2x to the other side and divide by 3, I can say that y is equivalent to 2/3 x. And now I'm just going to plug that in up here for y in the original equation. So I've got 2x squared plus 3 times parentheses 2/3 x squared minus 4 times 4x times 2/3 x equals 36. All of that. So I just replaced all the y values up here with 2/3 x. All right, well, now I'm just going to solve for x. I'm going to clean this up a little bit. So this term right here, we've got 4 over 9x squared times 3. That's going to be, let's see here, the 3 is going to cancel with the 9. So this is going to really be 4/3 x squared. And then this next term here, 4 times 2 is going to give me 8. So this is going to be, let's see here, negative 8x over negative 8 over 3 x squared. There we go. And then we still have a 36 on the other side. Well, this is actually kind of a nice situation because you'll notice that we have all x squareds on the left side. So we can combine like terms. Let's do these fractions first. So we've got 4/3 minus 8/3. That's negative 4/3. 2 is equivalent to 6/3. 6/3 minus 4/3 is going to give me 2/3. So we have a 2/3 x squared on the left side. Still have 36 on the right. Solving for x now, we can multiply both sides by 3 and divide by 2. Let me divide by 2 first. 36 divided by 2 is going to be 18 times 3 is 54. So we have x squared equals 54. So therefore, x is going to equal the square root of 54. Or you could call this, if you split this up into a 9 and a 6, you could call this 3 radical 6. Now you might be wondering, well, what about negative radical 6? Don't we have a plus or minus when we square root both sides of an equation? And yeah, you're right, we do, except that they said find the positive value of x. So we can just leave it as positive 3 radical 6 or radical 54 and call it a day. And now for the last part of a problem that has just kept the hits coming one after the other. Part D on this one. X and y are now both functions of time related by this equation. It's the same equation we started with, but here it is again, and now these are all functions of time. At time 1, the value of x is 2, the value of y is negative 2, the value of dy over dt is 4, and they want us to find the value of dx over dt at time 1. Okay, so this is just a related rates problem. We basically have to take the derivative of this whole thing with respect to time. So when we differentiate implicitly, our implicit functions are all going to have d letters over dt's attached to them. And we're just going to have to solve for dx over dt after we do all that differentiating. So let's start with differentiating. Starting on the left here, we've got 4x. And now since x is a function of time, I have to multiply it with the chain rule by dx over dt, the derivative of x with respect to time. Next, we have to do this 3y squared. That's going to be 6y times dy over dt. Minus, well, now we've got a product rule again. So box and ribbon time, we have negative 4x, positive y. And now the derivative here is going to be negative 4 dx over dt. And this one's going to be dy over dt. And let's see, using the ribbon to multiply that out, I have negative 4y dx over dt in whatever order you want to write them. And going the other way, we have negative 4x dy over dt. And all of that's going to equal the derivative of 36, which is still 0. Okay. So at this point, there's a few ways we could go. It looks like all of these are different, though. None of these are like terms. So at this point, it's time to plug in, and hopefully the only thing that we don't have a number for is this dx over dt, because that's what we're trying to solve for. Now, you might be wondering, well, what is up with this time t equals 1 business? Well, they're just telling you that you have to use the value of all these things when time equals 1. But they gave you the value of a whole bunch of stuff when time equals 1. They said at time 1, x is 2, y is negative 2, dy over dt is 4. And that's pretty much all the stuff you needed other than dx over dt. So going from left to right, we have 4 times the x value, 2, and dx over dt we don't know, so we're going to leave that around, plus 6 times the y value, negative 2, times dy over t value of 4, minus 4 times the y value of negative 2, dx over dt we don't know, so that hangs around, minus 4 times the x value, 2, and dy over dt again, that was 4. All of that equals 0. Let's go through and clean this up a bit. We're going to have to eventually solve for dx over dt, but it's just algebra at this point. So we've got 8 dx over dt, and this is going to be, let's see here, 6 times negative 2 is negative 12, then that's times 4, so negative 48. Next we have plus 8 dx over dt, and then we have, this is going to be minus 32. All that equals 0. Combining like terms, we have 8 dx over dt plus another 8 dx over dt. That's going to be 16 dx over dt. And the 48 and the 32 we can just add over on the other side. That's going to be 80 over there. So now just dividing both sides by 16 to isolate dx over dt, we end up with a value of 5.